40, negative 20. You could also do this with VI, where are we? A, VF, and D, and that would actually be using the VF squared equals VI squared plus 2AD and solve for D. So that works too. But efficiency, pressure during assessments, you should know this. All right, now here's a nice one. Calculate the ball's velocity at a time of 2.5 seconds. This is, when we talked about before, knowing your givens. It's not the peak, it's not the end, somewhere in between. And very important when we set up our givens. It's still a throw-up problem. Here we go. And so the simplest way in my mind of doing this is treating the problem like you would any other. Let's figure some stuff out. The VI is still 20 meters per second. The acceleration is still downward, when we called up positive, 9.81 meters per second squared. Now they're telling us the time is 2.5 seconds. Not at the peak, not at the end, just wherever it is, 2.5 seconds after the start, and they want to find the VF question mark. This, to me, is the most straightforward way to do it. There it is. Put your equation. VF, VI, A, and T. VF equals VI plus AT. Substitute in, I don't even think you need me to do it at this point, but substitute. So VF equals 20. Your negative is going to matter. Negative 9.81 times 2.5. And, well, let's solve this so we can talk about the answer. Solve 20, and this is about negative 10. It's a little bit different. Comes out about negative 5. Negative 4.5 meters per second. You may say, wait a minute, is that a reasonable answer? Well, negative means velocity. Means it's on the way down. At 2.5 seconds, is it on the way down? Well, yes. We already found that the peak is at 2 seconds. So we are now beyond the peak. We are on the way down. And so it makes sense that it's negative 4.5 meters per second. Now some of you may say, wait a minute. Could we just start at the peak and do this problem? Yes, you can. Now, if you don't know what I'm talking about right now, I wouldn't worry about it too much. This method is just fine. But an alternate to this, I don't think it's necessarily better or easier at all, but it gets you thinking. An alternate way to deal with this is do this from the peak to 2.5 seconds. How could that be? Well, if we know the peak is at 2 seconds, well then 2.5 seconds is only half second beyond the peak. And your givens in that case would be, at the peak, the VI is 0. The acceleration is still your, well heck, if you're going to do this, you could even call down positive at this point. So I'll put plus or minus 9.81, that's up to you. Your time now is not 2.5, but it's just 0.5, and the VF is the question mark. So, just another thing for you to think about. This method works perfectly well, but you also can use that symmetry of freefall and cut out the first half of the problem and just treat it from the peak on. Takes extra thinking, but it's a good kind of thinking. I don't recommend doing this problem this way, but it's nice to be able to realize, it's good to be able to realize that all of this is still true. That helps me at least feel convinced that you're getting these concepts. You should do it too. All right, what's the ball's acceleration at the peak? Need we really talk about it? At 3 seconds, need we really talk about it? A equals, depends what we call positive, of course, 9.81 meters per second squared down. I put a negative over there in the key for you because we've been calling up positive. It really is down. All right. How much does the ball's velocity change between 1.5 and 2.7 seconds? These problems are generally really easy if you follow the standard protocol. It's a throw-up problem, so we'll call up positive. I didn't give myself much room here. Let's give you much room. Givens with units. How much does the ball's velocity change? Change in velocity? Question mark. Now, yes, we know VI is 20. Heck, we know a whole bunch of things. Time to the peak, distance to the peak, or I don't know if we figured that one out. Actually, I think we did. Distance to the end, all these other things we know. But stick to what they're asking. Velocity change. You can list them all here, no problem. But don't ignore the question mark. The question mark is not V bar, it's not VI, it's not VF, it's delta V. How much does the ball's velocity change between 1.5 and 2.7 seconds? Now, if you ask me, easiest, most straightforward way to do this. They want delta V. They don't want to let us use any ink. Maybe I'll have to write it on the board. Oh, there we go. The acceleration. Let's try it. Oh, this is messy looking acceleration. The acceleration is, we're calling up positive, negative 9.81 meters per second squared. Now, this looks like an equation we know. A equals delta V over T. What does T mean? T means, if you look at your reference table, time interval. It is not absolute time. It is time interval. So if we go from 1.5 to 2.7 seconds, the time interval is actually 2.7 minus 1.5, which is 1.2 seconds. That's your time interval. And now it's a piece of cake. Equation, A equals delta V over T. And I don't know that you really need me to run this for you. Just plug it in. 9.81 negative equals delta V over 1.2. Cross multiply, you get your answer, negative 11.8, done. It's really a nice, straightforward problem if you're sharp with your givens. The other way that people do this, and also, I don't recommend you do it, but I do want you to understand it or realize it, just like here, there is an alternate. I do want you to realize it, which is, you could have said, now wait a minute, change in velocity, if I know velocity at 1.5 seconds, and I know velocity at 2.7 seconds, well, change in velocity is just your VF minus VI, or V2 minus V1. If you just subtracted these two, you would get your change in velocity. So you could actually do this problem, except for your givens, you'll have to do the whole problem twice. You'll do VF at 2.7 seconds, and you could figure that out, and then you could figure out your VF at 1.5 seconds. Using both of these, you would do VF equals VI plus AT, because you know the VI is 20 plus negative 9.81, and this is times 2.7. This one is 20 plus negative 9.81 times 1.5. You'll get two different numbers, subtract the two, there's also your delta V. So I don't actually recommend you do it this way, but I would like you to realize that that's another way to approach it. Okay, very last question, and then you're ready to conquer the world, the W36. How does air resistance affect the ball's maximum height? So here's the ball, it's fired upward. If you are moving upward, the air is, relative to you, pushing back. How will it affect the max height? It will decrease. D max. Put a question on the homework about what it does to the velocity and also what it does to the time in the air. So you can think about those there. But now you're ready for W36. W36 is the second sheet. This is more of a meat and potato, just grind through the problems with the givens, units, equations, substitute, solve, the guess formula. Okay, so I hope what you see here is more than one way to skin a cat, meaning you can solve these problems with multiple methods. But strong givens make for good solutions. Awareness of this symmetry of free fall makes for efficient problem solving. So, take this all seriously. Send me a message if you need it. I'll see you tomorrow.